So
theory and normal lab go butaro.
not the lab thing, whatever I gave, not Asha ma'am gave. Even I'm not asking about that. Oh, it's so many SS. So guys, please be honest. I may ask you to upload the pic now. You see, students, the first 90 people are very good. Most of them, they have done the homework. You see, this is very, very much increasing in that section. So what guys, you people should. So you let me down about 90 people. Sure. So I think we should start now. Thank you guys. A section people, they have done, I'm not done.
ಮನೆಗೆ ಹೋಗಿ ಬಿಟ್ಟಿಲ್ಲ ರಾತ್ರಿ ಕಾಲ್ ಮಾಡಿದ್ರು
ಏನಕ್ಕೆ
ಲ್ಯಾಬ್ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಹೋಗ್ತಿಲ್ಲ
ಅಯ್ಯೋ so then I should have handled A section then. Correct? No. They are more studious.
ATC ತಗೊಳ್ಬಿಡು
So I am start my call.
ಸ್ಕ್ರೀನ್ ವಿಸಿಬಲ್ ಹೇಳು
ಸ್ಕ್ರೀನ್ ಕಾಣಿಸ್ತಾ ಇದೆ ರೆಕಾರ್ಡಿಂಗ್ ಸ್ಟಾರ್ಟ್ ಮಾಡಿ So in the last class, we just completed the biasing part with the photo line, right? So next, today we have to see the light emitting line in LED. So you people know very much more than you about this. So I bet that you people can teach more. So with respect to this LED, what are the applications, why it is used, where it is used, all those things here, right? So let me in short give you the introduction for this one and what we have in the syllabus. Let's just see that one and it's one year this one. So since it's not at all what new to you, people are very familiar with this topic. So what exactly it is, and let's see only those things what is there for our syllabus. So this light emitting diode is a PN junction diode. Okay, so it works in the forward bias condition. So guys, let me take a pause. Let me know if anyone is facing any problem. So let me just have a look with the chat. Or can I continue? Hope everything is fine with anyone. Voice is not clear for the A section people. What about now? When that message was sent recent just now. Okay. So what about now, guys? A section people, is my voice clear and audible? So what about B and C? Where are you people? Are you here? No response from anyone. So can I continue? Is everything okay? Yeah, fine.
Not
so
clear
for the response. What about system is not clear for A section people?
ನಾನೇ ಕನೆಕ್ಟ್ ಆಗಿದೆ
Background voice. No, sir. Actually, the lab is quite
ಸೈಲೆನ್ಸ್ today.
background voice.
ಕೊಡ್ಲಾ
Getting half an hour.
ವಾಯ್ಸ್ ಇಸ್ ಬ್ರೇಕಿಂಗ್ ಜಾನ್ವಿ ಫ್ಯಾನ್ ಬೇಕಾ ಕಡಿಮೆ ಮಾಡಲಾ ಅವ್ರು ಬ್ಯಾಕ್ ವಾಯ್ಸ್ ಅಂತ ಹೇಳ್ತಿದ್ದಾರೆ.
Yeah, okay, guys. I think after a few minutes. Okay, so let's start. Okay, so if you A section people, if it's too much disturbing, you can stop me. Someone can unmute your mic and you people can stop me, okay? So let me just continue with those things. So LED stands for light emitting diode. Okay, so it is a PN junction diode which works with a forward biased mode. Okay, then what is the difference between a normal PN junction diode that works in forward biased and this LED? So usually what happens in the normal PN junction diode, whenever you apply some voltage, so the output you're going to get it in terms of voltage per current, correct? So whereas here what happens, so here when you keep input, you will get light as the output. So guys, let me just tell you, in the yesterday's class, we discussed about the photodiode where it's going to convert the input light energy into electrical energy, right? Whereas now we are talking about the vice versa procedure of diode where the electrical energy is converted into light. How is that possible? So it is possible by selecting the type of the semiconductor material. For example, so you know that. So energy neither be created nor be destroyed, right? So it's a basic rule, right? So it can only be transferred from one form to another form, right? Whenever the recombination of an electron or a hole takes place, so what happens? Some energy is liberated, correct? So that energy is liberated in the form of heat or light. Okay, so this is a very basic principle which you people already know. Okay, so that energy it cannot go anywhere. It can't go anywhere, right? So it will be converted in the form of heat or light. So if it gets converted into heat, then you will get the output in the form of voltage or current. If it gets converted into light, a light is emitted out of that circuit, correct? So if the semiconductor material what you have chosen to construct a PN junction diode, to construct a diode, if the semiconductor material what you are choosing is silicon or germanium, then what happens? The energy is liberated in the form of heat, so that you are going to get current or voltage as the output. Okay, if the semiconductor material used in the construction of PN junction diode is either silicon or germanium, then it works according to our conventional PN junction diode. If at all, if the material used in constructing the diode is gallium arsenide, gallium phosphide, gallium arsenide phosphide. For these type of materials, the energy, once the hole and electron recombination happens, the energy will be liberated in the form of light, and that light ray gets radiated from your PN junction diode. So I guess I made myself clear the difference between the normal PN junction diode that works in the forward biased mode and this LED which works in the forward biased mode. Okay. So how do we get that light here from this LED? It is because of the semiconductor material, whatever we have using. Either we are going to use GaAs, which is gallium arsenide or gallium phosphide or gallium arsenide phosphide. So then what are these? Which one you have to use? So you're going to use these material. So depending upon the light color, what you want to get out of this LED. So as and when the semiconductor material varies, the color of the light emitted varies. Okay, so you can have a chat and we are not going in depth of all those things. Okay, so any doubts so far? So I hope myself I made clear regarding the construction or what exactly an LED is. We have not yet seen the construction. What is an LED and how exactly, what's the difference between a normal diode as well as a LED, light emitting diode? Any doubts? Okay. So yes, let me tell you, A section people, first 90 people are very good, yeah. Okay. See, it's a fact. Okay. Coming to the construction. So, okay, I hope you people are not yet ready to receive the things So still you are in a sleepy mode or whatever it is. So let's just see, watch one video and we'll come back. So that those who are sleeping or those who are whatever you people are doing, stop sharing this playlist. Okay, so they will wake up. Stop. Screen sharing stop. You just have to be good. Google it. Okay, so now watch it carefully. I will ask someone, and you people have to explain this one because I know it. You people know it very well. Okay, first one. ಅದು ಕಾಪಿ ಅದನ್ನ ಪ್ಲೇ ಮಾಡು ಇದು ಕಾಪಿ ಮಾಡು ಕಾಪಿ ಲಿಂಕ್ ಕಳಿಸ್ತೀನಿ ಹಾಂ ಆಯ್ತಾ ಇದು ಕಾಪಿ ಇರ್ತದೆ ಇಲ್ಲಿ ಶೇರ್ ನೆಕ್ಸ್ಟ್ ಟೇಸ್ಟ್ ಮಾಡಿ guys, are you ready? Yeah, watch. So be ready to answer the questions. Volume up.
In simple terms, here's how an LED works. An LED is a basic semiconductor device, P-type semiconductor material containing positively charged carriers material containing negatively charged carriers called electrons to create a diode. When a current supply is connected to the diode, the negative charged electrons are forced to move one direction, and the positive holes move in the opposite direction. When a free electron comes near a hole, it combines. Holes exist at a lower energy level than the free electron, so the electron must lose energy to combine with the hole. This energy is released in the form of a photon, or a unit of light. The amount of photon energy released determines the frequency or color of the light. The type of material and process of creating the N-type and P-type materials dictate the color of the photons, as well as the efficiency and other performance characteristics of the LED. After processing the material into an LED chip, the chip is installed in a package that allows electrical connection and directs as much light as possible
So guys,
in
you
the
want us to
desired
replay
direction.
it? Or are you ready to answer the question? See, now also,
In simple terms, here's
and they gave the answer.
how an LED
See,
works.
see.
An LED is a
Replay.
Replay. Okay, so I got the response from them, and I'm considering the same response for the above 90 people also. Okay, so listen carefully.
In simple terms, here's how an LED works. An LED is a basic semiconductor device, P-type semiconductor material containing positively charged carriers called holes is combined with N-type semiconductor material containing negatively charged carriers called electrons to create a diode. When a current supply is connected to the diode, the negative charged electrons are forced to move one direction, and the positive holes move in the opposite direction. When a free electron comes near a hole, it combines with the hole. The holes exist at a lower energy level than the free electron, so the electron must lose energy to combine with the hole. This energy is released in the form of a photon, or a unit of light. The amount of photon energy released determines the frequency or color of the light. The type of material and process of creating the N-type and P-type materials dictate the color of the photons, as well as the efficiency and other performance characteristics of the LED. After processing the material into an LED chip, the chip is installed in a package that allows electrical connection and directs as much light as possible in the desired direction.
Okay, guys. Okay. So now who will tell me how the construction of LED is? Okay. So let me just go back to the notes and I will share you the construction. Okay. So here you have the construction part, and who will explain the construction? So definitely you are, so A section people, are you listening? So I asked who will explain us the construction. Okay. So definitely your effort doesn't go waste, definitely you'll fetch one extra marks. Lab or in study. Making note of your name is our responsibility, and keeping our promise is also our responsibility. Definitely, we are going to keep that. So, who will give us the construction now? So, you have to switch on your mic and you have to tell. No typing business. And make it fast. So, guys, attempt is important. So, if at all if you have understood, whatever you have understood, you just tell. You don't want? At least type that. Then we don't want. I just want to make sure that you people are with me. Then only I'll continue. Some response I want from you guys. I have shared the screen. You can see nobody is responding out of 79 or 77, whatever it is. Then what is the use that we give attendance for you guys? Yes, Prashant, what you're typing, type it fast. Now,
Multiple
where
users.
these fast A section people went? Huh?
ಹೋಗ್ಲಿ ಕೂರಿಸ್ತಾರೆ ಬೆಳಿಗ್ಗೆ ಅದಕ್ಕೆ ಹೋಗ್ತಾರೆ.
Semiconductor material used in ladies gallium arsenide. Yeah, very good. Next. Prashant, are you listen only more? Yeah. Prashant KG. Ubarkodana is
PN junction semiconductor diode.
PN junction semiconductor diode. Yeah, okay.
A lady works in forward bias.
Okay, very good. Mic is not working. Okay, Prashant, it's okay, it's okay.
A lady consisting
Okay, so
of PN
if I
junction
forget also
diode
to remember
units,
me,
P-type
okay?
poles
To
combined
remind
with N-type electrons to produce
Wow.
photons.
A-section people, you don't disappoint me. Yaar. Really consists of PN junction diode. Electrons to produce photons. Very good. Adish. Okay, the LED is a
ಏನು
PN
ಬೇರೆ
junction.
ಹೆಸರು ಬರ್ಕೊಂಡು
Okay. A combination of charge carrier. Okay. Electron photons. Yeah. Okay. Oh, okay, guys. But still, let me tell you, section people, they gave very good answer and most of them gave answer. Okay, and coming back to this Prashant and Prakriti's answer. Yeah. So, did I tell you that P material is placed above the N material? The answer is it's correct. Okay, so whatever you people have typed is correct. But I'm just very curious to know why do you think the P type material is placed above the N type material? So for A section people also, guys. So coming to the construction thing, okay. So you can just see here, okay, all of you. So this is how the construction is. When they ask during the examination, okay, guys, now stop typing and you just listen. Okay, so anyways, thank you all. Okay, so you can see the construction part here. If they ask in the examination, this is how you have to write it. Okay, so let me take up a page. I am supposed to use black colored pen, right? As you people do. Okay. So here, coming to the construction part, here you have a N-type material. So it's a P-N diode, right? So we need a P-type material and we need a N-type material. So here you can see the N-type material. Okay. N-type material. And here above this N-type material, so you have a P-type material. Okay. So as most of your friends have answered, so what we are going to do, so above the n-type material, we are going to use the p-type material. So because when the recombination takes place, so light is emitted at the surface because p material is at the surface and the emitted light is visible. Okay, so if you do the other way, if you place p side material below this n-type material, when the recombination takes place, so the light will be emitted since this p material is not at the top of this material, diode, whatever it is, so the light emitted is not visible to the outside world. Am I clear? So that's the reason why you will place p-type material above n-type material. Got it? So next, here you need the anode and cathode connection, right? So to get the anode connection, here for the p surface, you're going to coat it with the metal. Okay, so that metal, any metal, you can take aluminum, copper, or whatever. Okay, so a metal coating is done to take out the anode terminal. Why metal coating is done? Because we know metal are the very good conductors. That's why. Okay. So coming to the cathode connection, so here the top bottom surface of this N layer is coated with a gold layer. Okay, a gold film cathode coating is done here at the surface of this lower surface of this N material. From this, the cathode connection is taken out. Cathode connection. Okay, so what happens whenever this is connected in a forward biased mode. You can see here. What is the meaning of forward biased? If you have a PN junction, so this P-type material is connected to the positive terminal of the battery, and this N-type material is connected to the negative terminal of the battery. Where do we have P-type material here? This is the P-type material. This P-type material is connected to the positive terminal of the battery, and this N-type material is connected to the negative terminal of the battery. So now it is in the forward biased connection, correct? So when you connect this PN junction PN diode made up of carcinide, gallium arsenide or whatever it is. So when you connect this in the forward bias mode, the recombination takes place here. So what happens when you connect? The minority carriers electrons of the P type, majority carriers electrons of this N type gets attracted towards this positive terminal of the battery. So what happens? These electrons will start moving upwards towards the positive terminal of the battery, towards the P region, right? So it will start moving towards the P region. And similarly, what happens here? The majority carriers holes from P side and the minority carriers holes from the P side, they start moving towards the negative terminal of the battery. So this direction, it will start moving, correct? So meanwhile, this movement happens. So whenever a free electron finds a hole, the recombination takes place and the light is emitted, photon is emitted. Okay, so from this PN junction type. So this is the construction plus the working principle. So this is what is there in these two paragraphs. Am I clear? So moving on next. Yeah. Yeah, one more point. This diagram that is explaining, which you need to write it when it comes to the working. Okay. So here, what do you have? The same thing you have here also. Okay. So you have a diode here. Okay. So P-type you have connected to the forward and N-type you have connected to this one. And this is how the electrons will move and this is how the recombination takes place and the emitted, light is emitted, right? So now what happens? This working of the LED depends on the quantum theory. Okay. So this quantum theory, you will learn it. Some introduction portion is there for you in your 5th semester subject. Okay, so I think you have already heard. Now it's a buzzing word, right? So everywhere you will hear this quantum theory. Okay, so what exactly this quantum theory states? So whenever an electron change, whenever an electron changes its state from a higher energy level to a lower energy level. Whenever an electron jumps from a higher energy level to a lower energy level, light is emitted. This is what the quantum theory says, and you can see the same thing is happening here. So whatever the electrons that were there in the conduction level, conduction band, because of this positive forward biasing, whatever you have applied, so it jumps to the valence band because of the recombination. Okay, so here the recombination takes place, in which the electrons will jump from conduction band to the valence band. Okay, so this quantum theory says whenever the electrons move from higher energy level area to a lower energy area, photon is emitted, and here this photon is getting emitted. Okay, so this diagram you need to write, and you have to the same thing, whatever we discussed before. Okay, so this is here in the previous diagram. The photon emitted is not, this is your diagram you need to write for the construction, and this diagram you need to write for the one. Okay. And the energy of the photon is equal to the forbidden gap, energy gap, whatever that is present between this conduction band and valence band. And coming to the color that we have already discussed, it depends on the semiconductor material, whatever we have used. Okay. So coming to the application, you know that. So it see whenever the light is emitted, so to it actually emits the infrared light. Okay, applications. Okay, hale beginning. Okay, yes, guys. So for a moment, I'm not sharing the screen. Okay, yeah. Types of light. It emits an infrared light. So it emits some the emitted light could be a visible light or it could be an invisible light. Okay, so if it is if it emits an invisible light, then such LED. It depends on the semiconductor material again. Okay, so guys, let me make myself a bit clear. So this LED, it's going to emit infrared light. Okay, so that infrared light could be a visible light or invisible light. If at all that LED is emitting an invisible light, then such LEDs will be used in your remote control system. So you might have observed your TV remotes at your home, right? So there, that small LED will be there, but light will, whatever that IR light that is emitting from your remote, you can't see that. Correct. But nowadays, if you consider the whatever your DTH remotes and all, if you go to there, that LED blinks, right? So that LED emits visible light, visible IR rays. Okay. So I guess I'm clear now. So that coming to the applications of the LED, so it can be used in the remote control systems in which it emits a invisible light, IR. Okay, so it can be used electronic calculators for displaying digital data. So here it is visible light, it emits visible light. Okay, so next traffic signals, you know, you can write, no need to buy half the applications here, right? So you people know it very well. Where what are the applications that applications of LED, right? So it is used in digital computers to display computer data, in digital watches, automating heat lamps. You people can just increase this list, correct? No? So you people can go on writing a number of applications to this list. So if any doubts with this LED topic, so any doubts? Okay, so if you people don't have any doubts, we will move to the next topic. So section people, any doubts? So what about the background now? Is my voice clear now? Okay. No doubts. Okay. Thank you guys. Thank you. So let me move to the next topic. Okay. So coming to the next topic. So next topic is called as photo coupler. This photo coupler is also called as the opto coupler. Okay. So what exactly is this one? So guys, what are the things we have discussed? So guys, once again, you just excuse me. Take a break for.
Okay, guys, let's take the attendance. Type and keep your USs ready. Textbook and textbook ಇಲ್ಲ. Actually, this textbook PDF version is not available. We provide the notes. Okay, let's answer. Lesson 1.
So guys, coming to the PDF version is not there. As I told you, module
3.
1 PDF version we don't have. If at all, if anyone, few people are good in searching in net, if you get it,
5.
please share with me also. Okay, so but I have the old textbook
6.
which the topics will start from module 2.
7.
So that is there. So that definitely I'm going to share it with you, but that doesn't help much. Okay.
7. 7 absent. 8. 9. 10. 11. 12. 13. 14. 14. Anaka. Absent. 15 present. 16. 16. 17. 18. 19. 19. Ankita. 20. 19 present. 20 present. 21. 14. Where were you? In between, if you can, I can't turn the pages here.
So guys, be ready with your USs. I'm taking the attendance now.
21 present. 22. 23. 24. 25.
Okay. Today is 8th.
25.
Navya, Nayana,
26.
Nayana,
Bhargav.
Nilisha,
27.
Niharika. So guys, you have to respond. I think I'm not giving attendance on Niharika. Nayana, yeah, fine.
29.
Niket, Niket,
30.
Nikhil,
30. Chandan. He's absent. 31.
Nikhil is
31.
absent. Nitesh,
Chandrakant.
Nitesh is there. Omkar,
31 is also absent. 32.
Avinash. Avinash now joining the
26
conference.
present.
Sai Tarun,
31 absent. 32. Okay, 33. 34. 34.
Sai Tarun,
35.
he didn't attend yesterday
36.
also. Then
34.
Navtej is
Chirantan
present.
absent.
Given at Navtej. Sudarshan,
35. 36.
Pavan,
37. 38. 39.
Pavan, given.
39.
Nishant,
40.
given. Kaushika,
40. Vasant
given.
Reddy.
Yeah, Kaushika, given. Pradeep, yes.
Absent.
Pradeep is
41.
absent.
41, 42,
Prajakta,
43, 47 I have given.
Prajwal R,
43,
Prajwal R,
43, 43 absent.
Prajwal R is not there, absent.
45,
So tell him that
46,
he has not attended even one
46.
class also. Prakriti.
47, 46 absent.
So guys, if at all, if anyone is year back, something like that,
47.
year back won't come for your batch, right? Because if people have not taken the attendance exam. Prakriti P,
47,
Pranav M, KM,
Ritik Gaurav Maurya also
Pratana,
absent. 48,
P, Prashant,
49,
Pratik,
50,
Praveen,
50,
okay, Pritam,
Gurudarshan
Priti,
absent.
Prince,
51, 52,
Kritika,
52,
Prince,
Harish absent.
Prince didn't respond.
53,
Prince is absent. No, given Prince.
53,
Kritika, okay, Raghavendra,
55,
okay.
55.
So let me start.
I think 55.
Rohan,
58,
Rahul, sorry,
59,
7, 8, Rahul, yeah, Rahul Tripathi,
60,
Rajashekar,
60, 62, 63,
okay, Rakesh, Rakesh didn't attend yesterday's class also. Rakshita P,
absent.
okay, Rakshita P, okay, Maruti, Ranga, okay, Ranak, Hindu, okay, Gopal, Venugopal Reddy,
Wait.
Venugopal Reddy is
64,
absent.
65, 67, 68, 69,
He also
70,
didn't come
73,
yesterday.
73,
Rishabh,
76. Okay.
Ritik,
77,
Rohan,
77,
Rohit Patil,
77 is absent.
Rohan Gupta is absent.
77 is absent. 78 present, 79 present.
Rohit,
80, okay, 81, 82, 83,
Rohit
84,
FP.
84,
What about this Rohit FP?
absent.
Why he is
85,
not attending classes? Tarun Ram,
84 absent, 86,
yeah, given Sai Nagesh,
86, 87, 88,
okay, Samanvita,
89, 90,
Samarth, okay, Sandeep,
90, okay, 90 is not.
Sangana Gowda, okay, Saraswat, Sarthak, Sarvesh, okay, Shashank,
007 I am not present.
Vinapa,
40,
Shivam, are you there?
43,
Shivani, Shri, and Raj, Shivam, I didn't get reply from Shivam.
present.
So marking him absent.
26, 30,
Okay. Shreya, yeah, Shreya and
26
Shivani.
present, 30,
Okay.
Chandan
So
present.
next Shreya and
007
yeah,
I have given.
Shreya, Sindhu. Okay. What about Sindhu? Okay, Sindhu, Sonal, Saurav. Yeah, very good. Srajana. Okay, Srinidhi. Okay, guys. Sudrit. Very good. Suraj. Sushmita H.
Is 62 present. 67 also present.
Yum, okay. Yum is also joined.
Hey guys, please,
What about Sushmita
for
H?
attendance and all, don't message personally.
Okay, Shivam, given Shivam. Okay, why did you answer that
30,
time?
30 Chandan I have given.
Huh? What?
Okay, people were asking for soft copy or PDF version of the textbook. So
So there
the
is no
textbook
other
is
way. I
new
have to
version.
give correct.
The PDF,
Given. Okay, next Swatikeyan.
PDF is not available.
Tejas,
Okay, don't
Shyam,
worry.
Tejasvi,
Our only first module is theory like
Tarun,
this. From second module onwards, it's like
Diksha,
automatic only.
Usha,
Even if you take this soft copy of the textbook,
Tarun,
maximum of the problems are not solved. We only will solve and give the notes for all the 5 minutes. Don't worry about that. Still, if you want to refer the textbook,
Usha, Vaishnavi,
if you want, you
Tarun
can
given
search
sir.
our. We already provided the name of the textbook
So
and
what about
author.
Usha? Okay.
If you are very
Vaishnavi,
good in
two
searching and all,
Vaishnavis.
you search. If you
Am
find
I
even
very
power
good
ones
ones?
also,
Rashita, Vibham,
we'll make utilize of that.
Vansh,
If it is,
Rashita,
if you
Vibha,
are
I
not
didn't
getting,
get.
it's okay. Don't worry.
Vibha
You
marking
get
absent.
notes for all the 5 minutes.
Vishal, Vishnuvardhan, Vishwas, Vishal, Vishnuvardhan, Vishwas. Okay. Ravi, Yash, Yashaswini, Yukti. Ravi, Yash, Yashaswini, Yukti. Yukti, are you there? Yukti is absent. And Vivek. Okay. Tikshna. Tikshna, are you there? Okay. Okay, guys. Yeah, Nilisha given. I told no. So no need to, yeah, Tarun given. I told. Okay. So let's continue with our topic. Okay. So we are using this attendance business. Avinash, stop typing. Avinash, yeah, section, B section. ಹೇಳಪ್ಪ given no Sushmita. I told no giving for both Sushmitas. I give for Avinash also. I have given. Okay. So guys, let's. Yeah. Thank you. Attendance ಮಾತ್ರ ಎಷ್ಟು ಚೆನ್ನಾಗಿ ಕಾಲ್ ಮಾಡಿ ರೆಸ್ಪಾಂಡ್ ಮಾಡ್ತೀರಾ. Okay. So let's continue.
No, stop sharing.
Yes. So let me just. Okay, so we are continuing with the photocoupler, optocoupler. Okay, so what are the things we have seen? Photodiode. In photodiode, what happens? Oh yeah, sorry guys, I forgot to tell you the symbol of LED, right? Yeah, let me come to that portion. Okay, so in photodiode, what happens? Light energy is the input, electrical energy is the output. In LED, what happens? Electrical energy is the input, light energy is the output. So here coming to the symbol of the LED, you're going to write a normal PN junction diode where this is anode and where this is cathode. Okay, but what is the difference here? You will just write two arrows. Okay, so this represents the emitting of the light. So, but what was the symbol for photodiode? Here it takes the light. This was the difference. This is the difference between symbol of the photodiode and LED. Okay, fine. Okay, so those two things. And coming, who's that? Shivam, is there anything that you want to speak?
Recording on.
Recording. Yeah. So now you have understood what is photodiode and LED. So here what happens in the optocoupler. So here you can see in this diagram. So here you have a circuit, two circuits which are isolated, correct? So there is no connection between this first one as well as the second one. Okay. So what happens in this optocouplers, the data gets transferred between these two devices. So even though it is not connected, how's it possible? So the connection, how it gets established between these two. So this is what optocoupler is all about. So what happens? So here, whatever this first circuit which are taking it as a source, so this source emits light, and whatever the second circuit that you are going to take it, so this receives this light and it generates current or voltage. So am I making any sense to you guys? So what is this optocoupler? So here the energy gets transferred between two isolated circuits. So coming to the construction of this one, what now exactly this optocoupler is constructed. So here it always needs two components, right? So when it is considered as a source, So what is this source? This source is a photo generator. Okay, so normally this source will be considered as a LED which emits light. Okay, so you can see here this is an LED. Anode is connected to positive. You know LED works in forward bias. Okay, cathode is connected to negative. So which is that source that we normally use? We normally use LED as a source for this optocoupler. So this destination we are normally use because light is emitted, correct? So that light this circuit should receive. So we are going to make use of photodiode, photoconductors, photoresistors. So basically these are photo sensor devices. They are going to they are going to detect the presence of light. So how do you get light? This circuit emits light. This LED emits light, and this photo sensor, this could be photodiode. Photodiode is the only photo sensor that we have studied. So you can just write photodiode only. No, nothing will happen. Okay, so but in general, if you can remember, you can just write. So this circuit will be photo sensor, and that photo sensor could be photodiode, photoresistor, photoconductor, whatever it could be. Okay. So if you can't remember all those things, you can just simply write photodiode. Okay. So now these two photo generator and photo sensor will be isolated with the help of some dielectric isolator. Okay, so which is that isolator? You know, dielectric that we have discussed. It is the Si, silicon dioxide. So these two will be separated by silicon dioxide. So here you can see which is embedded in the IC in the below diagram. So here you have the photo generator. Here you have the photo sensor. Okay, so what happens whenever the see here you are going to apply the power. Okay, so to pin number 1. So here if you apply this positive terminal of the battery, then what happens? So this LED is in the on state and the light is going to emit. When the light emits here, so this is a photo sensor. This detects the light, and here it converts light energy to electrical energy, and you will have the output voltage. Am I clear? Okay, so this is how it works. So if you don't apply power to this pin number 1, then the LED will be off and it doesn't emit any light, and here it doesn't detects the light, and the output voltage is not produced. Okay. So now did you get the working of this optocoupler? Very easy, right? So what all you need to understand is the working of photodiode as well as the LED. That's it. You just club those things and you just write it. So guys, module 1 of ADE is very easy, right? Right? Okay, screen share agide Ashanu. Okay, okay. So I know it pretty well that your seniors, they have already left you with the impression that module 1 of ABE is very difficult, right? So don't listen to them, don't jump to any conclusions. See, you just need to learn only one story. What you're going to do is just repeating the same story according to the situation. That's it, correct? Okay, so all we know here is to 3 stories. So which are those? The first one is biasing. The same story we are going to apply it thrice for fixed bias, collector bias, as well as for voltage divider bias. So what is that story? Finding IC, finding VCE. So what is there in that story? First you need to apply KVL for input side, find out IB, then IC is equal to beta IB, find out IC, then apply KVL to output story. First story, remember. Okay, so what is the second story? Second story is all about working of P and I. What is forward biased? What is reverse biased? Forward bias, we are going to use it in LED. Reverse bias, we are going to use it in photodiode. Okay, so this optocoupler is nothing. So if you know those two, just see here, you have 2 different circuits where there is no connection, but still these 2 are working together. Data is getting transferred, right? Okay, so this is the story of this optocoupler. Okay, so LED will work in forward bias. This photodiode will work in reverse bias. So how exactly this forward bias is done? P side is connected to positive terminal, N side is connected to negative terminal. Here the okay, so P type is connected to negative terminal in reverse bias, N type is connected to positive terminal. Okay, so if you know these two stories, then you can make up this one. And moving on next, if you know the application of the op-amp, all the remaining topics will be very easy for you. Okay, so please don't jump to any conclusions before judging about this module 1 of ADE. It's really easy, it's really scoring. Only thing is you have to little bit of effort you need to put in. So that effort could be in memorizing the things or it could be in understanding the things. And that is left to you. Whether you want to understand it, well and good. If not, also it's okay. Don't worry, just memorize it. It's completely fine. Okay. So let me tell you, up to some portion, yes, you people, being a software engineers, you people don't need it. Yes, I agree, only up to some extent. Okay, so being a faculty, I'm not supposed to tell this one. But still, as far as the video exams is concerned, yes, you need to, if you're not understanding it, you need to scratch your head. If you really want to understand, you people can ask, we are ready to explain it how many times till you people get it. Okay, so if not, also don't scratch your head. Just know those three stories. And I hope that I myself have made clear with those three stories. Okay, so coming to the applications of this one, it's electrically noisy environment. Okay, so these are the applications where these photocouplers are used. Switch mode, power supply, signal isolation, power control, so input and output switching, PC, modem communication, controlling transistors. Okay, so these are the applications of the photocoupler. So guys, any doubts before we move on to the next topic, that is the multivibrators. Okay, so let me just pause and let me go back to the whiteboard. So any doubts for anyone? Am I clear with those two things, whatever we have discussed? Any doubts? No doubts. Everything is clear. Okay. So then it's a time to move further. Okay, stop typing. So now we are starting with the op amps. Okay. So let's postpone the introduction of the op amp till we complete this multivibrators. So first we'll see this timer circuits. What exactly this multi-vibrator is. Okay, so this is your first lab experiment. So please listen to the theory carefully because you need to write the design there. So if you know the design, then it will be easy for you to do the design there. So even if we change the values, the externals, you people can easily
in manner.
write it. ಇದು ನೋಡಿರಿ. ಇದನ್ನ ಕಳಿಸ್ತೀನಿ download. Okay. Okay. So what exactly this multi-vibrator? So this multi-vibrator is also called as wave shaping circuit. So what is this? So it is a circuit with regenerative feedback that produces a pulsed output. So what do you mean by pulsed output? So here it's a circuit that is. So here it is a circuit which is going to produce us a pulse output. Pulse output in the sense, you know pulse, the square pulse will be generated as a output. Okay, so how this output is going to, how the circuit generates this output? By using the feedback. Okay, so this is what the output of this wave shaping circuit or multi-vibrator is. So where exactly this will be used? So if at all, if you want to have a delay in the circuit, so they can be used in producing the delays and all, okay. So don't worry too much about all those things. So just understand that it is a pulse generator. If you want to generate pulse, you can make use of this multivibrators. Okay, so they are used to produce highly and accurate stable time delays. Okay, so time delays, if you want to generate, so they are capable of handling these time delays very well. Okay, so where this delay comes, so for example in your Java program or in your C program, so what you're going to do, so after doing some second, you know how fast these processors are, right? So within a fraction of second, within a nanosecond, the number of jobs, thousand number of jobs or whatever the number it will be done, right? So you want the processor to sleep for some time. So there what you're going to do, so you're going to make use of sleep, right? You will call this function. So I hope at least some of you have studied this one. Or you're going to make use of delay function. So what happens? So till that time your processor will be released. It's not going to execute that thread. That particular thread will be put on hold. Okay. Will it go yes, ಇವಾಗಿದೆ next time?
Fourth sem ಗೆ.
Okay. So okay. So this that pause thing, whatever you're going to call now, so that is going to happen. Okay. So here you can make use of these circuit. So anyway, we are not going to scratch our head how exactly it is done. But if it is going into your head, just try to connect between these things. Okay. So till this particular time, so till this is off, don't do anything. It's something like that. Okay. So to generate the delay for stable delay. So what do you mean by stable delay? So here when it is in the delay, so this shouldn't fluctuate. This noise shouldn't come. So if it is not stable, then the delay, the processor will get confused, right? So that stable delay, it should be stably, it should be there in this T off state. Okay, so that the thread is put in the pause condition. Okay, so only after 1 second or whatever the time that you have given, after 1 second, you want to remove this pause and you want to continue with the processing of this thread. Okay, so it's like that. Okay, so if you have not understood also, it's nothing important, just leave it. Okay, so here you have two types of multipliers. Okay, so basically we have three types. So here the first one is bistable multivibrator, monostable multivibrator, and astable multivibrator. What are the difference between these two? So bistable multivibrator is in which both the states are stable. So what is the meaning of it? So it means that, so I said that this is what the output that we are going to get. Correct. So here I can call this as a T on state. Correct. So this one I can call it as a T off state. Okay, so these are the two states because the output of these multivibrators are pulse output. Correct. So this T on state is one state of this pulse output. T off is one more state of this output. Okay. So here, if both these states, if T on state and T off state both are stable, then such multivibrators are called as bistable multivibrators. If only one state out of this T1 and T off, if any one state is stable, then it is called as monostable. You know, the meaning of mono is single, stable is only one state is stable. Okay, so single stable state is called as monostable. Bi means two, stable state. If both the states are stable, then you are going to call it as bistable. Then what is astable? So astable, A represents absent. A stands for absent. This you people will very well know from your English knowledge, right? So A means absent, stable means stable state. Absent of stable states leads to astable multivibrator. Got it? So what is the meaning of this one? What do you mean by stable state, or what exactly it means? So it means that, so in the monostable state, only one state is stable. Let's take that this T off state is stable. Okay, so always this device will be there in the T off state. Okay, so whenever an external trigger is applied, whenever an external pulse input is given, what happens? From the stable state T off, it goes to the T on for momentarily it goes. Okay, so it depends on the duty cycle. So it depends on the, so guys, I forgot that word, the duty cycle. It depends on the duty cycle. Momentarily it goes high and again it comes back to the off state. Okay, so this is what happens in mono state. So I hope I'm making sense. Stable state is T off state. So the circuit will remain in the T off state. When you give the external trigger, external input, it momentarily goes to the state T on, which depends on duty cycle, and it comes back to the stable state T off. Got it? So this is what monostable is. What happens in the bistable? Both the states are stable. So if the system is present in the off state, you need an external trigger to go to the on state. And this T-on is also stable. The circuit is capable of remaining in this T-on state. Once again, the trigger is applied. When the trigger is applied, it comes back to this one. Okay. Once again, when the next trigger is applied, it goes to the next state and it continues. What happens in the stable multi-vibrator? Here there is no need of external trigger. It can oscillate between T on and T off on its own. Hence, you can call this as stable multi-vibrators as oscillators. Okay, so they are capable of oscillating between the two states T on and T off. It can go on producing the state infinitely. Am I clear with the introduction of these three topics, bistable, monostable, and astable? And coming to our syllabus, so we have the working of monostable and astable. We don't have the working of bistable, so don't worry. But in the lab examination, they will ask it in the theory. So even in your theory, you are executing only astable. You do, so they are practicals. You are going to implement only astable multivibrator. We are not going to implement monostable. Okay, so let me repeat it. We have three types: bistable, monostable, astable. So bistable doesn't come into picture. Monostable, you have it in your theory. Okay, astable, you have it in your theory. Astable, you have it in your lab. Monostable, you don't have it in your lab. Bistable, you don't have it in your lab. Okay, so only in your viva you have to answer these two. But in the theory examination, you will get the working of both monostable and astable. So now today we are seeing the working of this monostable multivibrators and astable multivibrators, and then we are done. Okay. So guys, listen carefully. Here this we are making use of this 555 timer in order to build this. Very sir.
ಇಲ್ಲಿ ಡ್ರಾಯ್ ಟೈಪ್ ಮಾಡಬೇಕು ಅಂತ ಹಿಂಗೆ
ಪೇಂಟ್ ಹಾಕೊಂಡು ಮಾಡ್ತಾ ಇದ್ದೀನಿ. ಹೌದು, ಇದಕ್ಕೆ ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ ಬೈಗಾಡ್ ಬೆಸ್ಟ್ ನಮ್ಗೆ ಇಲ್ಲಿ ಅಪ್ಲೋಡ್ ಮಾಡ್ಕೊಂಡ್ರೆ. ಬಟ್ ನಾವು PPT ಮಾಡಿಲ್ಲ ಅಂತ
ಬರಿಬೋದು, ಬಟ್ ಜಾಗ ಸಾಕಾಗ
ಅದು ಸರಿ ಹೋಗಲ್ಲ, ಸಣ್ಣ ಕಾಣುತ್ತೆ, ಅವ್ರಿಗೆ ಕಾಣಿಸುತ್ತೆ. ಇದು ಸ್ಕ್ರೀನ್ ಶೇರಿಂಗ್ ಮಾಡಿ ಬೇಡ ಅನಿಲ್ ಸರ್,
ಸ್ಕ್ರೀನ್ ಶೇರ್ ಮಾಡ್ಬಿಟ್ಟು ಪ್ರೋಗ್ರಾಮ್ ಬರೆಯೋಕ್ಕಾಗಲ್ಲ ಅನ್ಸಿಲ್ಲ ಲೈನ್ಸ್.
ಬಟ್ ಅದು ಬರೆಯೋಕೆ ಸರಿ ಕಾಣಿಸುತ್ತೆ. ತಕ್ಷಣ ಇದು ಏನು
ಇವತ್ತು ನಮ್ಗೆ ಜೊತೆ ಇಲ್ಲ, ಅದೇ ಪ್ರಾಬ್ಲಮ್. ಸುಮ್ಮನೆ ಡ್ಯೂಟಿ ಇಲ್ಲದಿದ್ರೆ ಟಿವಿ ಹಾಕ್ಕೊಂಡ್ಬಿಡ್ತೀವಿ.
ಬರ್ತೀನಿ
ಎಷ್ಟು ಗಂಟೆಗೆ?
11:30.
ಬರ್ತೀನಿ ಬಿಡು.
ಆಶ್ರಮ ಬರ್ತೇನೆ.
ಮೊಬೈಲ್
ಬರ್ತೀನಿ ಬಿಡು. ನಿಂದಿದೆಯಲ್ಲ ಮೊಬೈಲ್.
ಸರಿ, ಮುಗಿಸ್ಲೇಬೇಕು ಇವತ್ತೇನು ನೋಡ್ಬೇಕು. ನಾನು ಬರೀ ಇದು ಮಾತ್ರ ಮುಗಿಯೋದು. Okay guys, so now we are discussing the working of monostable multivibrator. So just remember this monostable multivibrator, we are constructing it by using 555 timer IC. So what exactly this one? It is an IC, okay, timer IC. Okay, so 555 timer IC. So the inside view of this 555 timer IC is here. So this 555 timer IC it consists of two comparators. These two are op-amps. Okay, so it consists of two op-amps, one flip-flop. This is the flip-flop, SR flip-flop. Okay, so these two are op-amps. These op-amps are used as comparators here. So you will understand what is this. Okay, so it consists of three op-amps, it consists of flip-flop, it consists of transistor. Here you can see the transistor. Okay, so next, what do you have for constructing this monostable multivibrator? So here you can see the applied VCC. So to this VCC, so here is connected 3 5K resistors. So you know, whenever for a voltage, if you connect resistors like this, what is the job of this one? It's going to divide the voltage, correct? So because of these three 5 kilo ohm resistor, the voltage at this point, you can see at pin number 5 is two-third VCC. Okay, so the voltage at this point, so what is this? I told you this is a op amp, upper op amp, which is called here as comparator, the upper comparator, and we are talking about this voltage which is connected to the inverting terminal of this upper comparator. Okay, so the voltage at the inverting terminal of the upper comparator is two-third VCC. So guys, please listen to the story carefully. Okay, so next, because of this 5 kilo ohm resistor which are connected in series, the voltage at this point. Okay, so the voltage at this point, which point I'm talking about, the non-inverting terminal of the lower comparator. Okay, so the voltage at the non-inverting terminal of the lower comparator, the voltage at this point is one-third VCC. Okay, so what are the things we have said? I have just told you that this 555 timer IC consists of two comparators, and it consists of one flip-flop, it consists of one transistor. Still we have not jumped to the working of these things. It's okay, fine for the time being. Just understand it. So whatever the VCC that we have applied here, because of the presence of these three 5 kilo ohms resistors, the voltage at this point, which is that point, inverting terminal of the upper comparator is two-third VCC. The voltage at this point, what is that? Non-inverting terminal of the lower comparator is one-third VCC. So these 2 points, please keep in mind. Remember. Okay, so remember these 2 points. Yes. So coming to the working of this SR flip-flop, so this you have already studied in your previous semester. So in this semester, in the same subject, you're going to see the detailed working of this SR flip-flop. Okay, so what exactly this SR flip-flop, this much you people know it. Okay, so whether you know the remaining things or not, so this much you people are very, this you people know it very well, correct? So this is no change. Okay, so 0 0 no change, 0 1 q will be 0 because r is equal to 1 reset condition, 0 1, and this is set condition, q is 1 1 0, so this is invalid. So this will not come into picture. So why all those things? Let's see when we jump to digital. Okay, so for the time being, we just need to know when s is equal to 0, the flip-flop will be, q will be equal to 0. When s is equal to 1, q will be equal to 1. Okay. So this is what you need to remember to understand this one. Okay. So coming to the working of the comparator. So here, this comparator, you will have only 2 states. Okay. High state, low state. Okay. So only 2 output you will have here. So if the voltage applied at the positive terminal here, if it is more, then it will have high input. Okay, so if the voltage applied at the non-inverting terminal is more, then it will have low. Okay, so what happens here? Here the other, here also the same thing people can think. So here if this is greater, then it will be, if this is greater, then it will be 0. Why? Because here the input is applied to the inverting terminal. That's right. Okay, so don't worry too much about those things now. Okay, so just understand that the output of this one will be either 1 or 0, depending on the input. Okay, so that's enough for you for the time being. And coming to the transistor, you know how exactly the transistor works. Okay, and one more story what you need to understand here before starting is, here you have a capacitor and here you have a transistor. Okay, so what you need to remember is, if this transistor is on, so then what happens? This is the connection that gets established, correct? So whatever your VCC is there, so that will be here. This capacitor is disconnected. The capacitor is not charged. So this is what the story that you need to know. If this transistor is off, then there is no connection between here. This connection will not be there. So what happens? Whatever this VCC are applied, flows here, and this capacitor starts charging through R. Okay, so this is what the story you need to remember. Okay. Okay, guys. So these are the prerequisites that you need to understand the working of this 555 timer. So let me pause it, go back to the big blue button. Any doubt so far? You got it? You understood? So still I have not yet started how exactly that monostable multivibrator works. What I have told you, all the story that you need to understand the working of monostable. You understood? So I have just told you SR flip-flop which you have already learned. And I have just told you to know two things are there called as comparator. Their output will be either 0 or 1. Okay, and you know that the transistor is on, capacitor will charge. The transistor is off, capacitor will charge. So this is what you need to remember. Okay, so nobody is typing. So I'm thinking that you people are following me. So either two things will be there, right? So either you have understood everything that you don't have doubt, or you have not at all understood anything. Correct? So only two things are the reason. So maybe take it in my favor that you have understood everything. Yeah, people are typing, no doubts, understood everything, yeah. And I should believe. Okay, let me believe. It is in my favor also, okay? So let me believe that you people have understood everything. Let me start with the explanation for this one. Okay, so So what we are doing here is, so initially, let's assume that this flip-flop is in the set condition. Okay, so if it is in the set condition means what? So guys, I hope you are listening. So set condition means this Q is 1. And this, guys, I forgot to tell you, this is our output. Okay, output terminal is connected to pin number 3. Okay, so this Q bar is the output. Okay, so what are we assuming? Now we are starting with the explanation for working of this monostable multivibrator. I'm just assuming, I'm starting it with the assumption that this flip-flop is set. Set in the sense this Q is equal to 1. Okay, so Q is equal to 1. It is because S is equal to 1. Got it? So what is our output? Our output is Q bar. Because Q is equal to 1, our output is 0. So now we are here at our output. Okay, so now we are in the 0 state. Correct? So because this is equal to 1, this connection will be there, correct? So this connection will be there. Because of this connection, this transistor is on. This transistor is in the on condition. Because the transistor is in the on condition, this capacitor is not charging. And we are assuming that initially the capacitor is in the discharge state. So there is no charge present in the capacitor because this transistor is on. It's because I have assumed that this flip-flop is in the set condition. Okay. So now what we are going to do, we are going to apply a negative going trigger at this pin number 2. Okay. So what is this here? What do you mean by trigger? Trigger is just a pulse. Okay. So negative going trigger is I'm going to start apply this VCC. It will start from this VCC and it will go to a 0 and it will come back to the VCC momentarily. Okay, so momentarily it changes its state. That is what a trigger means, right? A negative going trigger. So what is this? This is a positive going trigger. Okay, so we will start from 0 and it reaches the VCC and it will come back to 0. Which is the positive going trigger. But what are we applying now? We are applying a negative going trigger at pin number 2. So now what happens when the voltage at this point is 1/3 VCC. Okay, so here what we have? Here we have 0. Correct? Okay, so what happens? From this VCC, here you will have somewhere here you will have 2/3 VCC. Correct? And here you will have 1/3 VCC. What you have done? the initial setup we have understood. So our output is in the 0. Okay, so when this trigger is applied, it will start from VCC, and at some point of time it falls below 2/3 VCC, correct? When it falls below 2/3 VCC, so here it becomes 0. Yes, becomes 0. What happens when RS is equal to 0? No change. Okay, so the circuit remains in the same state. What is that state? It is there on, transistor is on, the output is 0. Okay, so after falling below 2/3 VCC, after some time it falls below 1/3 VCC. Okay, so once it falls below 1/3 VCC, what happens? The voltage at this point becomes more negative. Okay, so no need to worry if you are not understanding it, just you get to this sentence. Okay, once the voltage falls below 1/3 VCC at this point, so here what happens, because this is more negative, so here the output of this will be 1. So once you say the output of this comparator is 1, so here R becomes 1. So because S is equal to 1, when R changes to 1, so then what happens? This flip-flop is in the reset condition. This output will go to 0 and Q bar will be 1 and our output will come to 1. Okay, so our output will come to high state. So because this output is 0, this transistor is in the off condition. So because the transistor is in the off condition, this capacitor starts charging towards VCC through the resistor RA. Got the story? So what is it? Let me just repeat it. So once the VCC falls, this trigger input falls below 1/3 VCC, this comparator changes the input at the inverting terminal falls below 1/3 VCC. The output of the lower comparator changes to 1. R becomes 1. Q becomes 0. Transistor is off. Q bar is 1. Our output goes to high state. Sorry, it is here. This is wrong. So now our output is on state. Transistor is off. Capacitor starts charging towards VCC. Got it? So this state will continue. So let me show you the. Okay, so this is the output. Okay, so now this is the trigger input. As soon as it falls below 1/3 VCC, you can see here the output goes on and this capacitor starts charging. Okay, so this state of this situation of the circuit will continue. So till the voltage at this other capacitor charges up to 2/3 VCC. You can see here. So this threshold pin is connected to this capacitor, correct? So once the capacitor charges to 2/3 VCC, then what happens? Once the value here goes above 2/3 VCC, so here the voltage at this point is 2/3 VCC. Once this voltage crosses this 2/3 VCC, okay, so what happens? So here, okay, before that I should tell here, once this voltage, this what happens in this negatively going trigger, after going back to 0, again it rises, correct? So once it rises, it goes above 1/3 VCC. Once it goes above 1/3 VCC, so here this changes 0. So because S is equal to 0, it once again goes to 0, 0 state. So this 0, 0 state they have not explained in your textbook. Okay, so if you are understanding it, well and good. Otherwise, if you want to memorize the things what is there in your textbook, no need to worry about the 0, 0 state. Okay, so 0, 0 state, the circuit remains unchanged. Okay, so once the voltage at this point 2/3 it goes above this 2/3 VCC, so this goes 1. Okay, so what happens? S becomes 1. We know that R is already in 0. So here there will be a change. Q becomes 1. Q bar becomes 0. So our output comes back to the stable state. So because Q is equal to 1, once again this transistor will be on. Capacitor stops charging. Okay, so because this transistor is on, capacitor starts discharging. Okay, and we got the output. And this same story will repeat when you apply the next pulse. Okay, so this is the circuit diagram, and this is the internal schematic diagram, and this is the output. These three diagrams you have to write if they ask. and all the explanation, whatever you had here, it is the things whatever I have explained. Okay. So there's any doubts here? Any doubts? Okay. I don't know whether you people are listening or not. Any doubts? Type it fast. No doubts, sir. I'm assuming that, oh no, ma'am. Yeah, thank you. So thank you for allowing me to move further. Okay. So let's move to the stable multivibrator before ending today's session. Let's see the working of the stable multivibrator. The same story. Okay. The only thing is here we don't have the external trigger. So there you can just see here we had an external trigger, right? So we had an external trigger at pin number 2. But now if you see that pin number 2 is connected to the capacitor. Okay. So as stable status, both the states are not stable and everything gets repeated. Here also you have two comparators, you have a flip-flop and you have a transistor. Correct? The same story, let's repeat. Okay. So what is the difference between that one and here? There you have an external trigger and here you don't have an external trigger. That's it. Okay. So let's start with the same assumption here. Okay. So let's see that this capacitor voltage, initially it is in the zero. Let's assume that initially the capacitor voltage is zero. Okay. So and then what happens here? The capacitor will charge to VCC through RE and RB. It charges through both the resistors. Okay. So what happens in the on time here? So let's assume that our output is in the on time. Okay. So since this is on, this is off, and this transistor is off, and the capacitor is charged. Okay. So once this capacitor charge, if it exceeds this 2/3 VCC, what happens? So this S value becomes 1, and this value will be 0, and this is 1, and this is 0. Okay. So this transistor is on and this capacitor stops charging. It starts discharging. You can see here. Okay, so this capacitor starts discharging and we have our output 0. Okay, so once this discharging of the capacitor, because you can see here in this diagram, so till where it is discharging, so till 1/3 VCC it is discharging. Okay. So once the voltage at the capacitor falls below 1/3 VCC, the voltage at this point becomes more negative. Okay, so meanwhile this has become 0, 0, no change. Okay. So the output of this comparator goes high, R becomes 1, Q becomes 0, Q bar becomes 1. Once again you will have the state and this becomes off. Capacitor from discharging, again it starts charging. Okay, so this portion, got it? And you have high one. So till where it charges, so till 2/3 VCC. What happens once the capacitor voltage reaches 2/3 VCC? The voltage at this point becomes more positive. So here this state changes to 1, and this will be 1, this will be 0, and this will be 1, this will be 0. Transistor is on, the capacitor discharge, and that's how it oscillates between the charging 2/3 VCC and 1/3 VCC. Got it? And that's how this on and off state you are going to get it. Okay. So guys, understood? Any doubts? Any doubts? So guys, we are seeing the okay. So now that we have understood the working of both a stable and monostable, let's derive the equations and let's wind up the session. Okay, because once again next week you won't remember all these explanations. So once again, without the explanation you won't understand this one. So let's derive the expression for Tion. Okay, so how exactly you're going to get the Tion period. So this I'm discussing for monospheral, and this is what you have in your textbook. So where they have skipped it, so here I have written it so that it will be easy for you to understand. Okay. PDF ಕಳಿಸಿದೆ ಅಲ್ವಾ ಅದು. Okay. So what exactly this one? Non-stable ಕೆಳಗಡೆ ಕೆಳಗಡೆ derivation. This one. ಅದೇ ಅದೇ okay. Yeah, what exactly you have here. So we know that I'm talking about the monostable now. Don't get confused, please. Okay, so I'm deriving for monostable. So here in Tion, what is Tion? It is the time taken by a capacitor to charge from 0 to 230 cc, correct? Okay, so the voltage across the capacitor is given by VC is equal to VCC into 1 minus e to the power of minus t by RC. So let's visit the diagram. So here this capacitor, this is the monostable circuit. So here the capacitor is charging through RE, correct? So this formula you can change it to VCC, applied voltage is VCC 1 minus e to the power of minus t. This R will be RA because it is charging through RA, correct? Okay. So now what is this VC? This VCC, this VC is nothing but the 2/3 VCC. That is the T on time period, correct? So this VCC to the LHS, you can replace it with 2/3 VCC. So here it remains as it is. So what you're going to do, if you want to simplify this one, so VCC on both sides gets cancelled. Okay. So what you're going to do, so if you send this, if you take this e to the power of minus this side, so here you will be left out with 1 minus, because VCC you have cancelled, this 2 by 3 will come to the RHS. 1 minus 2 by 3 will give you 1 by 3. So this is what you have present. So what you have, e to the power of minus p on divided by RA into C is equal to 1/3 VCC. So e to the power of minus x, you people very well know that you people can write it 1 divided by e to the power of x is equal to 1 by 3, correct? So I have just taken the reciprocal. So that I can write e to the power of x is equal to 3, correct? So you can see here, e to the power of x is equal to 3. You know how to simplify this one, you know very well. So T on divided by RAC is equal to log 3 base e, correct? So this is how E evaluates. Okay, from mathematics knowledge, people know it already. Okay, so what you can do, T on is equal to log 3 base e into RA, this denominator, and sending it to the numerator of the other side. Okay, so if you evaluate this log 3 basically, it gets evaluated to 1.09, something like that, so which you can write it as 1.1 RAC, and that's how you got this one. Okay, so guys, if you are having any doubts, you can revisit to the recording and you can cross check it. Okay, so still if you have not understood it, you can come back to me. I'm ready to explain it once again. Okay, so that is the explanation for monostable. Okay, so let's see the S table derivations. Okay, so ಅಲ್ಲಿ ಮೇಲ್ಗಡೆ ಕೆಳಗಡೆ ಹಾ ಇದು. Okay, so coming to the explanation of the S table derivation of the S table multivibrator. So you people know that you need to take up the what capacitor voltage, correct? So the capacitor voltage is VC is equal to, see, this is what the capacitor is, correct? So VC is equal to VCC into 1 minus e to the power of minus T divided by RC, just now like whatever we discussed. Okay, previous period. Okay, so the capacitor voltage is VC into this one. So this voltage is when we assume that initially the capacitor voltage is zero. Okay, so if it is in the discharge state. Okay, so if at all, if it has any initial voltage, so then its formula, capacitor voltage formula will be this one. Okay, so VC is equal to V final. What is VF? VF is the final voltage this capacitor is charging to. Okay, plus VI minus VF to the power of into e to the power of minus T by RC. Okay, so now we know that VF value is the, what is the final value? VF value is VCC. Okay, so that is the value to which it gets charged. Initial value is in the stable, we know it oscillates between 1/3 to 2/3. Okay, so that's why I can write here 2/3 VCC is equal to final voltage VCC plus initial voltage 1/3 VCC minus final voltage VCC. Okay, so into e to the power of minus T. Why here RA plus RB? Because in the diagram we know it charges, capacitor is charging because of both the resistors RA and RB. Got it? Okay, so that's why we are writing both RA plus RB. So nothing guys. So here I have already simplified here. You people will very easily understand. So if you send this VCC this side, so what happens? 2/3 VCC minus 1/3 VCC will give you minus 1/3 VCC. So here 1/3 minus 2/3 VCC into this one. Okay. So if you cancel VCC and this denominator and all, this is what you are going to get it. Okay. So if you just rearrange the terms, you will get this one. So 1/2 is equal to e to the power of e minus this one. Okay, so if you take the reciprocal, you can write it as e to the power of x is equal to 2. Again, Pc is equal to log 2 base e into Ra plus Rb into c. So which is evaluated to 0.693 into Ra plus Rb. Got it? So if you move to the TD expression, T of expression, so you know in the T of expression from VCC, the final point is 0, correct? So here you can write the capacitor voltage as 1/3 VCC, the final voltage is 0, initial voltage is 2/3 VCC minus 0 into TD. Again the same evaluation, here it goes 0 goes, here also the 0 goes. So LHS you have 1/3 VCC, to RHS you have 2/3 VCC into e to the power of minus 6. Okay, so if you cancel this VCC and denominator 3, okay, so if you take the reciprocal again, you will land with the same thing. So you can write TD as 0.693 into RB into RC. This is the expression for T off. The total time period is given by T on plus T off, which is nothing but 0.693 into RA plus 2RB into C. Okay, and frequency is nothing but 1/. So 1/t, if you take the reciprocal of this 1 by this much, so this is what you're going to get 1.44 divided by Ra plus 2Rb into C. So guys, this is all the expression. So beyond this one, you have something called as duty cycle. So what is this duty cycle? The duration at which, see, duty cycle formula is this one, T(on) divided by total time. So let's see this once again detail in the next class. Okay, so just remember duty cycle is nothing but the time duration that the circuit is in the on state divided by the total time. Okay, so this is the formula. Always it varies between 50% to 100%. Okay, so guys, I know I was a bit fast here. So it was because only the derivations, and that derivations you can revisit. So how much ever slow, if I go now, you people won't understand it. Definitely you people will be having some doubts in the derivation until and unless you solve it. Got it? Okay, so that's why I have completed the derivation. So if at all, if you want any, if you are having any doubts, you can revisit to the recording. Okay, until your doubt gets cleared